Good morning, I'm Alex Marty, Lab Group 6B with Colton Noble, and today we're doing Lab 5, Spherical Aberration. And before we get into the lab, I'm going to explain what spherical aberration is. Spherical aberration results from the fact that we use spherical surfaces on lenses, and it means that the focal length varies as we, with the pupil radius, so as we go further out on the lens. And what happens is if we have a positive lens, spherical aberration will cause the rays that are closest to the optical axis, the paraxial rays, to come to focus behind the outer rays, which are the marginal rays. And this distance between paraxial and marginal focus depends on the shape factor of the lens. And if we're using a plano-convex lens and we have the plano side first, it's contributing no refraction when we have collimated light, and that causes them to be further apart. And we have the convex side first, in which case both surfaces are contributing refraction and marginal and paraxial focus are together. Plot a ray fan plot of the error versus the pupil radius. Spherical aberration is a cubic function, and all these things that I just talked about we're going to demonstrate in the lab.
Good morning, I'm Colton, and like Alex said, we're talking about spherical aberration in the Hartmann screen today. And so what I'm going to do is briefly show you our lab setup and explain how we located the marginal focus of the 75mm lens that we chose for this experiment. So we have a laser aligned to one rail, and we have a steering mirror which redirects the laser beam back down this rail. And we did all this using previous alignment techniques that we learned in previous labs. And the real interesting thing about what we have here today is the 75mm focal length lens with a Hartmann screen. And basically all a Hartmann screen is just a disc or a circle with small holes cut out of it, which allows us to probe it with the laser beam. And so in order to establish the marginal focus, we steer the beam all the way to the outermost hole of the Hartmann screen. And as you can see right now, that projects a spot across through our microscope onto the wall. And so now what we're going to do is we're going to try to demonstrate how when we move the steering beam through the different holes, how the beam translates across the wall. And it should translate those spots in a cubic fashion. And what we're going to see is that the beams move across the wall, and then they're going to change direction, and they're going to go back to where they started. And as you can see, we have the crosshair aligned on the beam, and this means that we are now at the outermost hole of the opposite side of the Hartmann screen, which this establishes our marginal focus.
So I'm going to explain parts D and E of the lab, which were to measure the ray fan at marginal focus and to measure the longitudinal aberration. That's part E. Part D, measuring the ray fan, what we did is we have our same setup that Colton explained before, and what we do is we translate the mirror from side to side such that the beam goes through all of the holes on our plate. And as we move from hole to hole, we move the microscope this way along the rail, such that on the wall our spot moves and recenters itself across on the crosshair. And we record all of those positions on the microscope, and we plot those, and that gives us our ray fan. For the other part, measuring the longitudinal aberration, we do the same motion, moving the mirror back and forth to go through all of the holes on the plate. But instead of moving the mirror perpendicular to the rail, we move it longitudinally parallel to the rail to refocus or recenter the beam across the crosshairs. And again, we record all those positions and plot them relative to the mirror position. And now Colton is going to go ahead and explain those plots and show you what we got.
Okay, so like Alex said, we're going to show you the plots we got from taking his measurements, and we'll start with the transverse spherical aberration. And this is the ray fan, and this is sort of what we expect. We see a nice cubic fit, but one problem that we do see is that the curve does not go flat towards the center, and that's just due to defocus in the measurement. We can easily fit and subtract that, and we get a ray fan plot that looks flat in the middle. Our longitudinal aberration ray plot also looked pretty good. It looks nice and parabolic. It has a shape we expect. You can see that some of the points don't quite fall in where they should, but we expect that's because of the alignment sort of losing itself as we go through the lab. The stages are wobbling on themselves right now, so we're losing alignment as we go. So Alex just finished flipping the mirror around in its cell, flipping the lens around in its cell, and allowing the laser light to go through the convex side first. So now we're getting 2 refractions instead of 1 like we were in the plano case. And as you can see, we've got the blue line plotted here, and that's the maximum spherical, as we did when the laser light hit the plano side first. And the pink line represents the spherical aberration we got when we used the convex side first. As you can tell, it's about half. So this demonstrates how shape factor can improve the spherical aberration in your lens.
Alright, the last part of our lab is to take our lens prescription, and we can get that off of the Newport website, and put it into code 5. And what we're going to do is look in code 5 and look at the rayfan plots that the software gives us, and compare those to the 2 rayfan plots that we calculated in lab, and see how well we did, basically. So that's it for this week. I'm Alex Marty with Colton Noble, reporting from the moon.